Okay, good afternoon everybody. So this is the event we have all been waiting for. Welcome everyone. It gives me very great pleasure to have Sankar deliver this Subramaniam Chandrasekhar lectures on advances in graphene, Majorana Fermions and quantum computation. I'd like to say a few words about this very successful ICTS events around the Chandrasekhar lectures. So I just have a list of the past lectures to give you an idea of the type of landscape that we have covered. So these are lectures which are delivered by very eminent academicians on important new developments in their areas of speciality. The first lecture in any series is aimed at a general scientific audience. It's not a public lecture, but it's a colloquium level lecture, while the remaining 2-3 lectures are very technical and are aimed at specialists. A workshop is usually organized around the theme of the Chandrasekhar lectures, and this combination has turned out to be a great success. So the original idea of the Chandrasekhar lectures came from the Loeb lectures of Harvard, but we have this add-on of a workshop which has made it even more successful. So here are the lectures which other people have given. For example, a little while ago we had Nima Akani Hamid talk about quantum mechanics and space-time in the 21st century. Then last year Satya Majumdar, or in the earlier in the year, Satya Majumdar spoke of random matrix theory. Then we had lecture on turbulence by Uriel Frisch, applied string theory to condensed matter physics and fluid dynamics by Damson, quantum phases of matter, Subir Sachdev. Then there was a very beautiful talk by Ludwig Fadeev, and the standard model of cosmology by Lyman Page, who claimed that he has seen the birth of our universe. It was a beautiful talk. Then black holes, and the whole series was begun by my good friend and colleague Ashok Sen on extremal black holes. So with this brief introduction about what the Chandrasekhar lectures are and what has preceded this one, I'd like to introduce Sankar. So Sankar is the Richard Prange Chair in Physics and a distinguished university professor at the University of Maryland, the USA. He is also a fellow of the Joint Quantum Institute and the director of the Condensed Matter Theory Center at Maryland. He received his PhD from Brown University in 1979 and has been a faculty at the University of Maryland since 1980. His undergraduate is from Presidency College in Calcutta, and he was also born in Calcutta. So Sankar's research interests are very diverse. They range from the quantum theory of matter, statistical mechanics, and quantum information theory. His publications and expertise are very broad. He has a very impactful set of papers with a lot of impact. He has mentored 25 students and twice as many more postdocs. And the other areas of interest to him are many-body interacting quantum systems, topological quantum computation, fluctuations in financial markets, physics of high-speed transistors, and so on. So it's a great pleasure that Sankar has agreed to come here and give this talk, and also played a very important part in organizing this meeting around these Chandrasekhar lectures. And with this few words, I'd like to invite you on the stage to give you a certificate and a memento. Come. Thank you.
Thank you, Sven. Thank you very much.
And with these words, I think we can ask Sankar to give his talk. Yeah. Yeah, everything should be okay. Okay, Spender, thank you very much for your kind introduction. I also want to thank you for inviting me for this very esteemed lecture series, and I hope I do justice to it. I also want to thank Arindam and Krishnendu for doing an enormous amount of work to make this whole thing successful. The conference so far has been fantastically organized, and I know how much work it is to do this. And I'm grateful to all of you, ICTS staff, Spenta, Arindam, and Krishnendu, for making it possible. So as you know, I'm going to go give 3 talks. And today's talk is going to be a general talk on a colloquium level, where I will actually concentrate on 2 of the topics that will be covered in this conference: quantum computation with electron spin and with topological qubits. I probably will mention topological insulator in 1 or 2 places. I would not mention graphene in this one. My last talk will be on graphene. It will be a technical talk. I should say that topological quantum computation, non-Abelian anyons, is a highly technical subject, and I would stay away from highly technical topics in this talk. But this review article that some of us wrote, one of my co-authors is in the audience, Adi Stern, actually gives all the technical details. We put a lot of efforts in this review article, and is written at 2 levels. First part is broad for everybody, and that's where my talk will be. And then the second part is for the experts who want to learn the subject. The problem with this subject, this topological quantum computation non-Abelian anyons, as they are used in topological quantum computation, that you need kind of advanced topology, quantum field theory, topological quantum field theory, and knowledge about solid-state physics all coming together. So no book, no course, in fact, no set of books together can teach students or postdocs how to learn this subject. This was our motivation to write this article, and people should judge. But if you want to learn, this is the article to go to. So topological quantum computation is a paradigm, new paradigm, for quantum computation where the gate operations, I'm going to talk about quantum computation, but I want to introduce topological quantum computation right away. Quantum computation involves quantum gate operations, which are unitary operations. And here the gate operations involve braiding of some particles, quasi-particles. These are the quantum knots, space-time braids, space-time motion of particles around each other. This braiding is the quantum gate operation. You need the suitable physical system. And then if the suitable physical system has these unique quasi-particles, these quasi-particles have to be non-Abelian anyons. They also turn out to be emergent Majorana modes. Then you can do topological quantum computation. Okay, so we have to look for systems which have these particles, and then you have to then know how to initialize them, how to measure them, and how to braid them. Then you can do topological quantum computation. Its advantage is that, in principle, it has no decoherence. So when Steve Garvin, my friend, talked today, we discussed decoherence, and these qubits that they have in Yale have very long coherence time. 100 microseconds, which is really almost eternity. But in principle, as also in practice, it's a bit different. There is no decoherence at all. If the fault tolerance is guaranteed by physics, by some underlying topology of your quantum system. So that's very good. But the disadvantage is that we don't know if these systems exist in nature or if we can make these systems. I mean, theoretically, they exist, and this talk will describe what those physical systems are. But let me start with quantum computation itself. So as you all know, quantum computation is a paradigm of 21st century which kind of unleashes the full power of quantum mechanics. Use the natural resource of the many-body Hilbert space. As we know, the history of Homo sapiens has been that any time we develop understanding of some aspect of nature, eventually down the line, somebody managed to make money out of it. It's absolutely universal. Sometimes it took some time. That means whenever you understood some aspect of nature, it could be converted into technology. Sometimes it takes hundreds of years. Newton figured out Newton's laws and so on, and then the industrial revolution that happened, and then laws of thermodynamics, industrial revolutions based on that, then Maxwell's laws. Again, the connection is not direct. Connection is very, very non-direct. But if you look at the history of technology, you'll find that understanding of nature always led to understanding of some resource in nature. So
engines are based on entropy and free energy. And so quantum mechanics has some resources, linear superposition and quantum entanglement. Steve talked about them. Those resources are not used in any technology yet. And the hope is quantum computation is one thing we know that will use those resources. So it has this exponential advantage of 2 to the power n over n in going from n classical bits, to classical two-level system to n qubits, and quantum two-level system. It's exponential speed up if you can use it. Well, I'm not going to actually talk about what it can be put to use for, because that will take us too far from physics, but it's a resource, and quantum computation uses this resource. Okay? So if you can controllably manipulate these qubits, these quantum two-level systems, and use their linear superposition and quantum entanglement, you can do quantum computation. But the problem is that you have quantum decoherence. We learned early that if you prepare a quantum state, in most situations, in all situations, eventually the quantum state goes away because it decoheres, it couples to the environment, and basically the quantum state doesn't remain pure, it dephases. So you have to do quantum error correction, and that quantum error correction is very hard. In fact, the birth of quantum computation is a theorem that quantum error correction can be done. So how does quantum computation go? It's a paradigm with 4 key ingredients. I'm going to go through this pretty fast. You have a Hilbert space, which is filled with these quantum bits, this quantum two-level system. They span the Hilbert space. And the new feature of qubit, of course, is that classical bit 0, 1, that's all you have. It is either 0 or 1. As you know, if a quantum spin could be up and down, let's say in z direction, but you can also have the spin in x direction or y direction. So you can have something which is kind of in between 0 and 1, but the number of possibilities in between the 0 and 1 is in some sense infinite. That's the power of quantum bit. So, so this is what Steve was talking about. You can have this entangled cat alive, poison vial untouched, and cat dead, poison vial open, this superposition, and that's what allows you to do quantum computation. So if you initialize these states, you have to put them in a known state. That's the first step. First, you need a system which has two-level quantum states. Then you initialize it, put all of them in some known state. What the state is doesn't matter. And then what you do, you just do the unitary evolution. You use some operator, unitary operator, you just do e to the power IHT. Now you may say, okay, what is that u? Well, what that u is, that's your code. So what that u is depends on what problem you want to solve, So just as you write a code, if you want to do an integral or a differential equation or a matrix inversion, this u will be suitably chosen depending on what your code is. And then the theorem says that if you do the correct coding, then of course you create a combination of all possible states. You measure the state, final state. When you measure, it chooses one possibility out of this huge Hilbert space, exponentially large number of possibilities. And what we know is that this state either solves your problem, or you can go back and do it very fast, and in algebraic time you solve the problem. So that's quantum computation. So it's very simple. You start with your initialized state, do quantum evolution on it, measure it, you are done. Okay. The problem is that the states cannot decohere in this time. So there are many proposed qubits. Also, the leading qubits are, and there was a time when I started in this field. That's even before Michel or Charlie or Amir. 1998, it was pretty amazing. We'll go to these conferences, the organization that support all of it in the United States. There'll be 300 people. So all 300 people know of one two-level system somewhere that they read as undergraduate, and they're sending a proposal saying this two-level system can be a quantum computer, and they'll be funded. So these meetings will have 300 people. There are many, many more candidates, but now the leading candidates are ion traps in atomic type physics, and Steve's favorite system, the superconducting qubit, okay, in the solid state system. But I'll talk mostly about electron spin. Basically, all these systems have one thing in common. They have quantum two-level systems which can be manipulated from outside, and their coherence is not very bad.
What was the difference between red and blue?
These are atomic systems that I don't care about, and these are solid state systems that I care about. Okay. I mean, you ask me a question, you get an honest answer. Okay. So problem is, of course, error, right? Because quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. And, so they couple to the environment. And because they couple to the environment, you have to do error correction. By the way, all computations depend on error correction. the reason computer science exists is there are theorems called threshold theorems which show that any error can be corrected. It may take many steps, but it can be corrected. You would not have computation if there was no error correction possibility. So some fraction of computer scientists basically prove theorems saying that errors can be corrected. And the subject of quantum computation started with Peter Shor and others proving, Steen and others proving, that in quantum problem also errors can be corrected. This was a watershed event. Feynman is one of the, probably has among the highest cachet of all physicists ever. And Feynman was talking about quantum computation early in the 80s. I can tell you no one paid any attention. I mean, now everybody talks about how great he was. In those days, we all thought that, well, he has earned his right to talk about whatever he wants to talk about. But we did not pay attention. Why didn't we pay attention? I remember having a discussion with Rolf Landauer. And he and I were exactly of the same opinion that quantum decoherence is continuous. It can never be corrected. There can never be a threshold theorem for quantum decoherence. So what Feynman is talking about is true for a Hilbert space, but it's not true for any laboratory. Because in laboratory, these two-level systems will decay, and it can't be corrected. And so, no, I can tell you, nobody paid attention to even Feynman, let alone Deutsch and so on. All of this changed when in 1984, Peter Shor and others showed, for me it was an amazing revelation, that actually quantum decoherence can be corrected. I don't want to get into how. All the quantum decoherence is continuous. You can correct it in some discrete manner, and there is a threshold as long as you reach the threshold. And this started the subject. If you can correct the error, then there is a theorem that says quantum computation is possible. Then you can start thinking, are there physical systems which can do that? I'm going to talk about how quantum error correction is done. Part of it is like classical error correction, the way this computer does error correction. You have multiple copies, redundancy basically. So if a bit flips, it puts it back. Here, if a bit flips, you just put it back. That part is like regular error correction, but continuous errors correcting, it takes a little bit more work, but it can be done. Okay, and there is another problem in quantum mechanics. When you measure, that's a big error because the set goes there. But all of these errors can be corrected at a computer science level. Theorems have been proven. And, this is just an example of how you do it. But it's very hard in practice. In fact, I do not know of any actual practical qubit where anybody has implemented error correction in any reasonable manner. It's very, very hard. And it's not clear it can be done, really, for anything, which can actually do anything. This is an open question, because when you look at the quantum error correction threshold theorems, there are lots of assumptions going in, and it's not clear that the laboratory system can obey those assumptions. It's not clear that it could not either. So it's a very difficult thing. So let me give you some example of what I mean by this difficulty. So let's talk about my favorite qubit in solid state, which is favorite qubit of at least 3 other individuals in this room, Charlie Marcus, Amir Jacobi, Michel Simmons, which is spin. A spin is an ideal qubit, right? We teach two-level quantum physics by calling it spin. If you go to textbooks, actually most textbooks don't have a chapter called two-level dynamics. They call it spin dynamics. And so spin is up and down, but it's quantum up and down. So you can start with, let's say, electron spin. So you start with some input state where, let's say, 0, 1, 0, 1, 0, 1, or all 0, all 1. And then you do your unitary operation. You have some Hamiltonian coupling the spins. You do the particular set of operation that solves your problem. Then quantum mechanics tells us that you get a horribly entangled state which involves all the possible combinations that you can have. But then when you do a measurement, it projects out one particular state. And if you have done this part right, with very high probability, this final set solves your problem. And if it doesn't, then you go back and do the whole thing again. And Peter Shor showed that at least for problems and Grover showed for a different problem, and there are other examples, that in algebraic time you will get a solution. And these unitary operations are very simple for spin. So it's either spin rotation, because you can rotate spins, or you need 2 qubit, 1 qubit, and 2 qubit operation. You have some spin coupling, let's say Heisenberg coupling, and you have to just entangle them and disentangle them. By the way, just as in classical computer science, there are theorems saying classical computation is universal, meaning all you need is certain gates. If you have those gates, anybody can do computation. Similar theorems have been proven in quantum computation, and it has been shown that all you need is a universal 1 qubit gate and universal 2 qubit gate. You can solve all problems, okay? And in spin, those are done, one by spin rotation, can be done by number of techniques, but I'll talk about the exchange coupling. That's not the only possibility. There are other possibilities. You can have, for example, dipolar coupling, but you need some kind of coupling so that you can entangle 2 spins and then disentangle them. So that's how you go from 2 to the power n to 2 to the power n. These are the quantum gate operations. So quantum decoherence is going to happen. So the proposals that were there, now there are variations on that, one based on gallium arsenide, one based on silicon. All of them somehow have single localized electron spin. Where the single localized electron spin arises from, I'm going to talk in a minute. And if you have one single localized electron spin, that's a qubit, spin up and down. If you have many of them, you can couple them, you have many qubits then. And the original proposal was in gallium arsenide by Daniel Loss and David DiVincenzo. Daniel is now at Basel, DiVincenzo at Aachen. And then Bruce Kane modified it for silicon, and people work on both of these, and they have relative advantages and disadvantages. But let me emphasize, for this to work, this error correction theorem says that the coherence time, which I'm calling Tm here, actually this number is more like probably million, not 10 to the power 4. So it has to be that much longer than gate operation. And so, this is assuming everything else is perfect. I'm not going to talk much about error correction. So, for example, the system I'll talk first, let's say take gallium arsenide. You put a quantum dot here. A quantum dot is just like a large atom. You confine an electron here, put another quantum dot, confine electron here. So this is your 2 qubit. I'm not going to talk about single triplet qubit. I'm just going to talk about original exchange qubit. I want to keep things simple. So you have one electron here. That's a qubit. Single qubit operation you can do. One electron here, single qubit operation you can do. And there is a gate here. You can control the tunneling. And this tunneling controls the Heisenberg coupling. You can do 2 qubit operation. And these things can now routinely be done. And in fact, I would not be surprised at all if in Charlie's laboratory and Amir's laboratory, this sort of confining electron in this qubit, in these quantum dots, and this kind of manipulation is going on right now. Students are doing it right now. And first question I'll ask is, okay, so what does the Hamiltonian look like? Here is one electron, here is the other electron. The Hamiltonian we're talking about, you apply a magnetic field. So spin couples to the magnetic field, each spin. And then you have some kind of coupling between the two spins, Heisenberg coupling, they couple with each other. Okay, and then the quantum gates, unitary operation is just this e to the power minus IHT. And that is it. That's literally, this is all you need in quantum computation. You don't need anything more than that. First question I'm going to ask, is it really true if you put one electron here in a quantum dot, another electron in a quantum dot, you really get a Hamiltonian as simple as this? It's not obvious that that's what you're going to get. There may be many more corrections that you have to worry about. So I want to do a hard calculation to show that. This is not a question you can answer just conceptually, thinking deeply. So here is my quantum dot, one quantum dot here, one quantum dot there, some artificial potential you create by applying electric field from outside, gates and so on, one electron sitting here, one electron sitting there. Now this you can think of now as an artificial molecule, size 500 angstrom, that has 2 electrons. So it's a 2 electron molecule. Instead of being 1 angstrom in size, this 500 angstroms in size, and it has some effective mass, some background dielectric constant. You have to take those things back on. So this is very early work of Shudong Hu when he was a postdoc at Maryland. We took this and we did a full quantum chemistry configuration interaction calculation. We said, okay, this is a molecule. So you can do calculations that people do for molecules. You know, this institute has a great tradition in chemistry. And we just did a quantum chemistry calculation, very large quantum chemistry calculation to get the whole spectrum. So this is the spectrum. And you see this levels here, you see they're separated from all these other levels. So this is the qubit space. So this shows that although there are many, many, many levels, not just 2 levels, there is a well-defined gap separating the low-lying spectrum from everything else, and this is your qubit space. This is the space you'll be working on. So as long as your energy scale, your temperature, all those things are small compared with here, let's say, of the order of 5 MeV, you are safe. You have a 2 qubit thing. Any correction has to be exponential. You can calculate the exchange coupling, which is just the single triplet energy separation as a function of magnetic field for various barrier size. So you can see that one can control this tunnel coupling, which is the exchange splitting, the J in the Heisenberg coupling pretty well. So the basic picture works. You do have an exchange coupling between these 2 electrons, and you can control that by controlling this gate or by changing magnetic field. What happens if you have more than 1 electron? You know, 1 electron per dot is easy. So that's just a 2 electron molecule. What if you have a 6 electron molecule, 3 electron in each? Because when we were doing these things, it was not clear that you can put 1 electron per dot, this calculation. Now we know one can do that routinely. So we also looked at, this was a conceptual question, it was not clear at all. But we showed in this work, this is 2005 I think, that as long as you have, your valence shell has odd number of electrons, so as long as you have like 3 or 5, you can do the same calculation, and I'm not going to go through the details, but you always have a qubit space. What happens is that as you put more and more electrons per dot, the energy separation between your qubit and the other levels goes down, okay? By the way, those of you who know chemistry know that in a multi-electron molecule, you do not have the theorem that singlet is always lower in energy than triplet. In a multi-electron molecule, I think ammonia, triplet is lower in energy, or some other. There are many, many, many molecules where triplet is lower energy than singlet. This oxygen, for example, right? Many, So we are very happy when we see this. We didn't know much chemistry. Chemists told us this is routine in chemistry. But for quantum computation, doesn't matter whether the triplet is low or singlet is low. It's irrelevant. Okay, all you need is a qubit space. So you can see that it goes negative even at zero magnetic field. That's fine. All you need is a qubit space, and we showed that as long as you have one electron on the top shell, so it's an odd, everything is fine. And I think Charlie told me that he's going to. There has been huge development in this recent days for reasons I'm not going to get into. This may have some huge advantage over that one electron per dot simple situation, but I will not discuss this today. We are actually doing a lot of work on it. We have gone way beyond this calculation. We have gone all the way to 14 electrons now, and there may be some advantages that perhaps will be discussed tomorrow. So one other question let's ask. All right, so you have a qubit space, but you're going to do manipulation, and there are all these other states. So there'll be some leakage. Well, you know adiabatic theorem. If you do things very slowly, you don't need to worry about those other levels. How slow must it be? All it has to be slow compared with the inverse of this energy separation, right? This is what we learn in quantum mechanics. As long as you're slow compared with the inverse of the energy separation, you are safe, you'll be the same. So you said do it infinitely slowly. You cannot do it infinitely slowly because you have decoherence. Quantum computation is difficult because you're always squeezed between these two needs. You got to do things slowly so that you have adiabaticity, because no real system in a laboratory will ever be purely two-level system. So you have to do things slow compared with some energy scale, and you have to do things fast compared with some other time scale, which is your decoherence time. So is there a space like that in this problem? Since we have the whole spectrum, Shudang Hu and I answered this question. We basically directly tested if the adiabatic theorem that you have in your textbooks is valid for this concrete system. And so we solved the problem. Shudang solved the problem with the whole spectrum we have. And again, I'm not going to go into these details. All I'll tell you, we found there is a well-defined regime where you can be adiabatic and you can be fast compared with your coherence time, at least for spins. So this qubit is a very good qubit for experimenters to look at. You can do things slow enough compared with your energy level separation, but fast enough compared with decoherence, everything is fine. What about silicon? I'm going to talk a little bit about silicon. A lot of people are working on silicon. Silicon has some enormous advantage. So, but I'll tell you what disadvantage silicon has. What I'm trying to point out is that quantum computation is an umbrella. It's like an excuse for us to do a lot of interesting science that perhaps could not have been done otherwise. So there are people, like recently Daikanov posted a paper on the internet savagely attacking quantum computation. And he missed the whole point. Quantum computation is kind of a goal. It's like the goal of Spencer Wadia and his cousins to figure the ultimate theory of nature. Okay, so ultimate theory. What is the ultimate theory? That's a goal, right? Ultimate theory do not know, but in looking for ultimate theory, you have a lot of achievements as you do that. Okay, quantum computation is like that. Quantum computation allows us to ask questions about quantum physics that we could not have otherwise asked, and we stumbled upon this thing. So let's say in silicon, the qubit is a bit different. In silicon, the qubit is you put phosphorus atoms in silicon, localized phosphorus atoms, and they create little hydrogen orbit. They create little hydrogen atom. The electron in the outer orbit of phosphorus becomes free, and it's called just a donor state, and it moves around. It's purely hydrogenic state. And that would be the qubit according to Bruce Kane, and in Michel Simmons' center, this is being studied in great depth. So you have this phosphorus atom, so you can solve for the Schrodinger equation. Is a phosphorus atom, electron is moving around, this is your qubit. Okay, this is your qubit. But this qubit is in silicon. It's in silicon, and you can calculate the exchange coupling. By the way, it's a beautiful paper. All the students should read this paper. Analytic, exact asymptotic form for the exchange coupling in hydrogen. It really is a beautiful paper. Okay, so we wanted to see what happens in silicon, and silicon. You cannot use this calculation of Herring because silicon is not in vacuum. You have to take into account the actual electronic structure, and we took into account actual electronic structure. Silicon has the 6 equivalent conduction band minima, so you have 6 possibilities. So you have to take a linear combination of these 6 states. That's how silicon works. This is just what nature gave you. So your starting state is going to be linear combination of 6 states, this 6 equivalent minimum. Ground state has this 6 equivalent minimum. So starting state is an arbitrary combination of those, and you put them in. What do you get when you put them in? You'll get trigonometric contribution coming from these 6 terms. What does this mean? So you'll have this term. That means there'll be very strong oscillations in this J that you did not have with hydrogen atom, because hydrogen atom, there's just one term. There was no trigonometric term at all, but here there'll be trigonometric term whenever this k minus k prime, where k being this vector, the vector reciprocal space that defines this minima, which are 85% out to the Brillouin zone. And so what we found, and it's amazing that nobody talked about it in spite of this huge amount of study for phosphorus and silicon, what we found was that the exchange will actually oscillate very strongly as a function of interdonor distance, because what happens is that unless you put the two phosphorus atoms exactly at equivalent site, that means k minus k prime is exactly 0, if they're slightly inequivalent, you have these oscillations. Okay? Only when you put them exactly at the right corner, they would not oscillate. Well, that's essentially impossible to do. Michel is trying to do that using an AFM tip, but even with an AFM tip, you are not going to be able to put all your atoms, all your things exactly at this point. Maybe you can put it here, maybe you can put it here, but not exactly here. And whenever you're not putting it exactly there, you're going to get these oscillations coming from these trigonometric terms. So that means when you make this silicon array of phosphorus atom in there, many of your exchange coupling, interqubit coupling, will vanish. So you do a quantum computer to characterize every qubit out of this 10 million qubits you put in. That's a nightmare, because characterizing that probably is an NP-complete problem. It's going to go. So this problem still doesn't have any solution. But I'm just pointing this out, that all this physics comes up because we are asking, would a quantum computer work? I mean, we are not at a stage where, and it's arising from the fact that ground state of silicon has this 6-fold value degeneracy arising from its band structure. And there are various solutions you're thinking about. Okay, let me now talk about decoherence. So Steve talked about T1 decoherence, which is relaxation, spin up becomes spin down. It turns out for spin qubit, this process is very, very slow. Many milliseconds, maybe even seconds, and you can actually prolong this coherence time just by lowering temperature, because for this you need some energy loss, phonons or something. So we don't really worry about T1 process at all. What we worry about is T2 processes. So T2 process is when the electron spin dephases. It doesn't relax. So what happens is that, classically speaking, it's still going around in the same way, but this simple harmonic motion is sometimes faster, sometimes slower, like I tried to do here. This animation that is going fast or slow is dephasing. Okay, and this dephasing is the big problem. And it's I'm not going to talk about T2 star. Never mind T2 star. That's inhomogeneous broadening. It's of the order of microsecond. Could be hundreds of microseconds. We'll see what it is. So there are lots of mechanisms that dephase. What is dephasing? That's a decoherence mechanism. You put electron spin. Anything this electron spin couples to in the environment, anything that you do not care about, is going to dephase it. The word decoherence basically means part of the Hamiltonian we do not care about. Because if you solve the problem exactly, there is no dephasing or decoherence in quantum mechanics, right? Called stationary state. It always remains in the state. But the problem in the laboratory, the experimentalist concentrates on the part of the Hamiltonian he controls. And there is a huge number, an infinite set of terms in the full Hamiltonian that the experimentalist doesn't control. And the electron spin would couple to all of them. And if that coupling is strong, there'll be strong dephasing. So some of the terms that we know is direct hyperfine coupling of the electron spin to surrounding nuclear spins, hyperfine coupling to unintentional impurities, dipolar flip-flops of the surrounding nuclear spins, spectral diffusion, I'm going to talk about it, dipolar coupling to other spin qubits in the system, dipolar coupling to unintentional bound electrons, any other spin that you have in the system, electron spin will couple to and cause decoherence. So, and charge fluctuations. Now you say, why should charge fluctuation matter? This is spin. Spin doesn't couple to charge. Well, the problem is, this is not just pure spin. Our Heisenberg coupling arose from exchange coupling. And as you know, in solid state physics, spin-spin coupling is very weak. Spin-spin coupling has C in the denominator somewhere, okay? So all spin-spin coupling that shows up in solid state physics that anybody studies is not a direct spin-spin coupling, almost all of them. They're all some kind of coupling mediated by Coulomb interaction. As you know, exchange coupling is mediated by Coulomb interaction. So this is exchange coupling. So if you have some other charge here that's fluctuating, this barrier and this potential minimum will fluctuate. That means the exchange coupling will fluctuate. And it turns out, I think that experimentalists believe, Amir, correct me if I'm wrong, this is a very important mechanism now preventing further progress of spin qubit, because there are lots of charges in semiconductors which move around, hop around, and they're making this potential barrier fluctuate. At that fluctuates, everything about this qubit is fluctuating, and that fluctuator causes dephasing. I'm not going to talk about it because it's not that interesting to talk about theoretically. Experimentally, it's a very difficult problem. Let me talk about this dipolar flip-flop mechanism, which I love talking about because I learned this whole thing, never came across this in any course I took. So let's say that you have, talking about a silicon spin, this is my silicon spin angular momentum, okay? It's very large because the gyromagnetic factor for electron spin is very large, and these are all the surrounding nuclear spins, okay? So you have one electron spin in silicon, and I don't know how many of you know, normal silicon is an isotopic mixture of silicon-29 nuclei, silicon-28 nuclei, and actually silicon-30 nuclei, okay? Now, silicon-28 nuclei and silicon-30 nuclei have no free spins. Silicon-29 nuclei have a free spin. It's much smaller because gyromagnetic ratio is 2,000 times smaller. But what happens is that the direct coupling between electron spin and nuclear spin is very weak in silicon. In gallium arsenide is strong. But these two nuclear spins talk to each other through dipolar coupling. So what can happen is that these two nuclear spins can flip-flop. One could go up and one could go down due to dipolar coupling. Now, the total spin is preserved. What does that do? Think classically. If you think classically, each of these nuclear spin is creating a tiny magnetic field at the electron spin, right? So as these things are fluctuating, what's happening? What is this electron spin seeing classically? It's seeing a temporally fluctuating background magnetic field. Because the electron spin doesn't know, let's say electron spin doesn't know there is a Hamiltonian controlling these nuclear spins, or every time two nuclear spins go flip-flop, the magnetic field is changing here slightly. So the electron spin is seeing a temporary fluctuating magnetic field, which to it looks random, but it's not random at all. It's extremely non-Markovian. Why? Because it's controlled by a Hamiltonian, very well-defined Hamiltonian. So what is that Hamiltonian? Well, the Hamiltonian here is that you have electron Zeeman energy because of a magnetic field. You have nuclear Zeeman energy. Look at the energy scale. I told you that they differ by a factor of 2,000. Then you have the hyperfine coupling between electron spin and nuclear spin, direct hyperfine coupling, which I'm not ignoring for this purpose. And then there is this flip-flop mechanism. The nuclear spins are flip-flopping. The time scale goes from 10 square to 10 to the power 4, 1 nanokelvin to kelvins. Any problem that involves so many time scales is a very hard problem. This problem was unsolved. This problem was identified in 1950s by stalwarts like Erwin Hahn. It remained unsolved. It's only the push by quantum computation led to its solution. I would say the first real solution was done by my student, Wayne Witzel, who was actually an undergraduate computer science student, but he wanted to work on quantum computation, and so his computer science skill was just unbelievably strong. He basically solved this problem exactly by using computer science skills. So what you have to do is that you have this Hamiltonian, and you have to basically ask how it evolves, and so this is a total Hamiltonian. We are just talking about this flip-flop part. We have to solve this problem. So you have to talk about some experiments. Suppose you're doing spin echo, like Steve talked about. So you can write down what the density matrix is, and you want to solve this density matrix, including all the nuclear spins. And Wayne Witzel developed a cluster spin summation technique. Literally, he did brute force summation of all the spins in this quantum dot, something like 10 million spins. You may say, how can you do that? If you think about it, normally it's impossible to do, but it's a combinatorics problem. And computer scientists basically solve combinatorics problem. And he solved this combinatorics problem basically exactly. That was 5-6 years ago. Now improved techniques have come up. You may think, what's the big problem? Why can't you do it perturbatively? The reason you cannot do it perturbatively, standard Wick's theorem doesn't really apply to spins. So you have to really come up with some other technique. And we did. I'm not going to talk about this technique. I'm going to show you. So basically, you have to solve the trace of this unitary operator in that full nuclear spin environment. We did that, and this is the result for Hahn spin echo. Experiment already was done. Each plot is for different angles. Silicon has an isotropic coupling, spin coupling. So each plot is for different angle. You are measuring along different around different axes on the silicon surface compared with 1-1-1 surface. And the agreement is very good. This is now the standard theory. This is, as you can see, from 2007. Everybody accepts it. But how can you make this go longer? Hahn spin echo takes away all the inhomogeneous burning. Can you do better? So people know that you can do better. You can use lots of pulses. Basic idea is that if you understand your Hamiltonian precisely, remember I told you, there is no decoherence in real life, right? In ideally, because decoherence means you don't know part of your Hamiltonian, you call it decoherence. Here we know what the Hamiltonian is. So you should be able to engineer pulses which fight this decoherence, okay? You use pulses to generate the electron so that it stays coherent, and there is a whole huge subject of this is called dynamical decoupling. Send external pulses to decouple the electron from the bath, and let me show you some of those results. So this was for gallium arsenide, this was silicon phosphorus, and this is, we're just using one pulse, it's called Horn spin echo, 2 pulses called CPMG, 4 pulse CPMG, 6 pulse CPMG. What you are seeing is this spin is decaying very fast. The decay time is 50 microsecond in gallium arsenide, you know, some 500 microsecond in 500 microsecond in silicon. But as you use more and more pulses, do more and more dynamical decoupling, you have no decoherence for a very long time. This one you see, you have no decoherence, and you can continue. And this is not just theory. Now people in the laboratory it has been verified that these things work. And this is not quantum error correction, because this is hardware-based quantum error correction. What we are doing here is keeping the qubit coherent for a very, very long time, because we understand the Hamiltonian that is decohering it very well. Okay? So this is now, but problem is that I'm not sure, even after doing all those things, we can reach the quantum computation threshold theorem. You know, the threshold is it's like 10 to the minus 6. It's not clear to me it can be done. Maybe it can be done, maybe it cannot be. So this is a central problem of quantum computation. We don't really know whether quantum error correction can really be done, both hardware-based, like I was telling you, dynamical decoupling and so on, and software-based using quantum error correction, many qubit and so on and so forth. So we need a plan B, just to be safe. This plan B was pointed out by Alexei Kitaev when I think he was in elementary school or something like that, long time ago. He was following the quantum computation procedure, and he knew topology very, very well. And I'm going to rephrase now, looking back, one can correct the history. He asked basically a rhetorical question. He said, well, the way quantum error correction goes is that what we are doing, each qubit, if it was perfect, would be called logical qubit, because you can do quantum logic operation with that. But I told you that it decoheres, so to have one logical qubit, you'll need many physical qubits. That's quantum error correction. You know, you may need 10, you may need 10,000. We don't know how many you would need. Depends on the error. So many physical qubits lead to only one logical qubit. So what you're using redundancy to do quantum error correction. This is what we do in classical computation also. Alexei understood there is another way redundancy occurs in nature. Again, I'm simplifying everything for a colloquium, where local geometry is a redundant way of encoding topology. Many different visual geometric structures have the same topology. I'm going to give you some simple example, but let's accept it that topology, like logical qubit, can be encoded in local geometry just as a logical qubit can be encoded in many physical qubits. So Alexei Kitaev asked this rhetorical question that if a physical system were to have quantum topological, which have to be necessarily non-local, because topology is a non-local study of geometry, topological degrees of freedom, which then they'll be insensitive to local probes because it's non-local, okay? Then information contained in them would be automatically protected against errors caused by local interactions with the environment. This would be fault tolerance guaranteed by physics at the hardware level with no further need for quantum error correction. This is topological protection. This is the memory. This is, my paraphrasing of Alexei's work over a 10-year period. This is basically the rhetorical question he asked. Jimmy, do you have a question? No. And let me give you a trivial example. This is taken from our Physics Today article that Chetan Nayak, Michael Friedman, and I wrote. By the way, I'm not showing references and not giving credit either to others or to me, because this is a high-level talk. This is all reasonably old work. So the example we gave is that to a topologist, a coffee cup and a donut are identical objects. Although in real life they're very different objects, because both have one handle or one hole or one puncture, as the topologists will say. And you can go continuously from a coffee cup to a donut, and this picture exemplifies what it is. Both of them from a topological viewpoint are identical. They both have just one puncture, as a topologist will say. We need the quantum donut basically. Okay, this is classical, and this is just an example how geometry is redundantly encoding. And as you know, this donut, the fact that it has one hole, one handle, it's very difficult to get rid of it. You have to really tear it completely. If you just take a little bite here, you can still see the hole. If you take a larger bite, you can still see the hole, because this is a non-local object. This hole is a product of the whole geometry, and you really have to tear the whole thing, do huge non-local vowels to get rid of it. And this is what Kitaev was thinking about, okay? Something like this, if it could happen in quantum mechanics, then you will have topological memory, which will be immune. A little perturbation here is not going to do anything, okay? it turns out things like this can exist. In fact, now it's a very big subject, and there are many different topological phases of matter. The specific phase that I'm interested in is the ground state of a system. Imagine a system, a quantum system. It turns out these systems are always interacting systems, the systems that I have in mind. There are other kind of topological phases like topological insulator, which are non-interacting, but this one is interacting. But interacting or not doesn't matter. I have a ground state of a system which has degenerate states, separate from other states by finite energy gap. This degeneracy does not arise from any symmetry. Normally, when you have degeneracy, like hydrogen atom has degeneracy, it arises from various symmetries. Some of those symmetries may be hidden. But this degeneracy doesn't arise from any symmetry in the Hamiltonian. This degeneracy is a topological degeneracy. If you have a system like that, whether you can have a system like that or not is a different question. If you have a system like that, it turns out then you can form a qubit in this ground state, because all you have to do is to do a unitary evolution. You start from some state in this degenerate subspace, do an unitary evolution to go to the other state. This can work as a qubit. So now the question is, can you have a quantum system which has a ground set quantum degeneracy, which is topological, not symmetry induced? This is a very big subject right now. It's probably the dominant subject in condensed matter physics. In many different aspects, it turns out that this sort of thing happens. So this new thing that has happened, and I think we'll have several talks, at least I know Joel already talked about it in the school. So this new thing that has happened is we're classifying phases based on symmetry, rather than, we used to always classify phases based on symmetry. This is the great paradigm in condensed matter physics, LGW, Landau-Ginzburg-Wilson. Incredibly successful paradigm. But this new paradigm that's emerging is that instead of symmetry, you classify phases based on topology. We know one phase of matter where this has already happened, that's quantum Hall. So quantum Hall, fractional quantum Hall, and then topological insulator now. These are all, there is no symmetry-related argument there, they're all topological phases. And this topological phase, as this picture is showing, is stable against an adiabatic The reason it's stable is that there is a discrete number underlying this topology. It could be Chern number or some other number. And whenever a discrete number cannot change slowly. Discrete number only can change discontinuously. And that's what the immunity comes from. You have to do some finite amount of thing to change 1 to 0. And all of these systems have some discrete numbers underlying that. What the discrete number is arises from different kinds of physics and math, but there is always. And sometimes these phases, and we know when, can host fractional quasi-particle excitations. If that happens, then you can do topological quantum computation. It doesn't always host fractional quasi-particle excitations. Like ordinary topological insulator, bismuth selenide doesn't, you have to do something to it. If this happens, you can do it. And then it's very simple what you do. This is taken from the cover of a Scientific American article that they wrote on this. Once you create this qubit, these quasi-particles, which turn out to be also Majorana mode that I'll talk about tomorrow, and you create them, you put them in a particular state by measuring their state by some kind of Aronoff-Bohm interferometry. Once you have done that, then you have to do the unitary operation. This unitary operation just turns out to be taking these and braiding them, taking them around each other. Very different from what ordinary qubits do. Then you measure their final state by Aronoff-Bohm, you are done. But there is a problem. I'm talking about solid-state physics. Our Hamiltonian is known. This is our Hamiltonian. Every system that Charlie Marcus or G. Eisenstein works with, this is the Hamiltonian. Electron kinetic energy, ion kinetic energy, electron-electron interaction, ion-ion interaction, electron-ion interaction. You know, I'm leaving out a few terms. Our Hamiltonian is exactly known, and you can look at it. It is not topologically invariant. If I change Ri to Ri plus x, if I stretch it or rotate it, it changes. The Hamiltonian does not have any topological invariance. So that means it must be symmetry. I'm calling it symmetry. I should have put a quote, not symmetry. This invariance that I'm talking about, it must be emergent at low energies. It cannot be, something that arising from the Hamiltonian. And so in a topological phase of matter, at low temperatures, energies, and long distances, the system is insensitive to local perturbations. In fact, to any notion of length. If I want to use jargon, there is no metric here at all. Okay, this is really a realization of Witten's famous topological quantum field theory. So I just want to make an anecdotal comment here. It's kind of qualitatively inverse of a fundamental principle in physics that has dominated physics over the last 50 years, spontaneous symmetry breaking. Spontaneous symmetry breaking, you have a Hamiltonian which has more symmetry than your ground state. Right? Ground state has less symmetry than a Hamiltonian. Here I'm talking about a state where the ground state in some sense has more symmetry. Ground state has this topological invariance that the Hamiltonian doesn't have. So it's kind of inverse here, okay, this topological thing. And the point is that we do not know the necessary conditions for a physical system to have the appropriate low energy quantum topological properties needed for fault tolerant quantum computation. It's simply unknown. If you give me a Hamiltonian, some complicated interacting Hamiltonian, there is no recipe I have or anybody has, I mean, I'm not very smart, but there are people like Mike Friedman who's very, very smart, or Adi Stern. He could not just look at it and say, this will have topological degree of freedom. Only way to do that is by solving the problem and looking at the wave function. Well, if you can solve the problem, then you of course know everything. So we do not know how to do it. In some aspects of sufficient conditions are known using conformal field theory. You, for example, know that your system belongs to certain conformal field theory, certain topological quantum field theory. We know if it's SU to level 2, it's Majorana Fermion. If it's SU to level 3, it's Fibonacci. But that's just word. If I give you a Hamiltonian, you don't know which conformal field theory belongs to. Again, you have to solve the problem. So this is an open question. Given a Hamiltonian, we cannot solve this. We have to be very clever. We have to somehow guess the wave function and then give powerful arguments why you believe the physical system belongs to that wave function, and then somebody has to do an experiment to show that it does. So, but that of course would not solve, would not stop theorists from coming up with these proposals all the time, and we do, because, so the key questions are what? We have key questions. For spin qubits, which I talked about first, the key question is, can you do quantum error correction? Is that feasible? If you cannot do quantum error correction, forget quantum computation. This is true not only for spin qubit, it's true for superconducting qubit, it's true for ion trap qubit, it's true for everything. Without quantum error correction, there is no quantum computation. Just as without classical error correction, there is no classical computation. So this is the key question for those of us who are interested in engineering a quantum computer. For topological quantum computation, you do not need to worry about the error correction, but here you have to worry about, does the matter exist? Is there appropriate topological matter where these particles exist with this grounds of topological degeneracy? Okay, if it exists, you can do everything. Now you may ask, this to sound like completely different way of doing things. This is like undergraduate physics, 2-electron molecule, 6-electron molecule, certainly undergraduate physics for smart students. And this I just told you, beyond graduate math, graduate physics, it's connected with Witten's 1988 paper. How can these two things be equivalent? Mathematicians have proven, Michael Friedman has a theorem, that these two approaches are equivalent, meaning they're universal. Any problem this can solve, this can solve. Any problem this can solve, this can solve. What has not been totally resolved is the question of efficiency. They may not be able to solve both equally efficiently, One may take forever to do it, but we know there is just one universal quantum computer, and both of these approaches are completely equivalent. I do not understand this theorem very well, so don't ask me any of the details, but Mike completely assures me that's not a problem. Now, these two are doing things. I'm going to give you an analogy, which I stole from Leon Balance, is that it's like noise reduction versus deafness. When you're listening to music, you have noise. And there are two ways to be immune to noise, right? One is you use this Bose headphone and all those things, you do noise reduction. That's this error correction. Another way is that you could just be deaf. Then noise is not going to do anything to you. And that's the second approach, where you're immune to noise, okay? This is, so, yeah, but music was not a good example. I knew somebody would say that, okay? Let's say music is not the point. Let's say you're like Adi Stern. You cannot work if there is noise. You see, Adi could keep his door completely open and work if he was deaf, because noise would not influence him. I think let's talk about working in your office, and there's a lot of noise outside. People are playing soccer and so on. You can put Bose headphones, noise cancellation, or you can be deaf. That's a better example, okay? So, well, I'm going to tell you, I'm going to answer this question now. What happened to my, so I'm going to answer this question now. I'm going to move over to now topological. It exists. It has been seen in the laboratory. That's the claim. Here is the qubit. Hey, I'm not making it up. Go to Google and Google Majorana and Delft. You will see hundreds, perhaps thousands of hits showing you how a quantum computer is just around the corner. This is a very famous experiment done in Leo Kornhaven's group last year. It was this paper came out, I believe, in April in Science. Is the fastest published paper in Science, apparently in its history, between submission and actual publication. Okay? I can tell you that the referees were contacted and referees are forced to send back report in 24 hours. I can absolutely guarantee that. Okay? Not just one referee, all three referees, okay?
Sankar Das
You got it, man. I was trying to hide, but...
How many days from submission to publication?
Say it again.
How many days from submission?
It came online, I think, in 11 days. Yeah, came online. Yeah. So what it is, this I'm going to talk about in great details tomorrow. Okay. What is being measured? Let me tell you what the measurement is. Measurement is exactly the same measurement Jim Eisenstein was talking about today. It's a differential conductance measurement of tunneling conductance as a function of a voltage. So it's very standard measurement people do in semiconductor and superconductor. And this is a superconductor. You see, this is the superconducting gap. Usually at 0 voltage, nothing should happen. It's a gap. You're really deep inside the superconducting gap. Theoretical prediction was there should be a peak at that 0 voltage. And this peak is this funny object, a Majorana qubit. And this was theoretically predicted. That's why people believe it to be. It was theoretically predicted. I'm going to talk about it. This is the paper. And there are various proposed architectures for doing topological quantum computation. Let me just tell you all of them, except for these suitable magnetic lattices or Kitaev lattice, which nobody is really pursuing. All of them are equivalent to this Majorana Fermion I mentioned. So this is a very important subject. All of them are equivalent. And they are all equivalent to this chiral PF superconductor, which I'm going to spend a few minutes explaining. Once you have them, then all you do is create the particles, braid them, measure, you are done. Quantum computation is done. Okay. Let me leave out all these details about. So the most important ones are things that have already been mentioned in this conference. A 5-half fractional quantum Hall state is one. Reed and Green showed that's equivalent to chiral PF superconductor. We propose that real-life chiral PF superconductor, strontium-ruthenate can be used in some circumstance. You have to go to very low temperature. Fu and Kane in a seminal paper pointed out you can combine topological insulator with SF superconductor proximity effect, and then J. Sau in Maryland simplified it, showing that spin-orbit coupled semiconductor. You don't even need a topological insulator. Because as you know, topological insulator is a beautiful subject. Only problem right now is the systems are not quite insulator. There's a lot of crappy bulk conduction because of various defects, and as long as you have that, your Majorana will leak away. So Jay came up with the idea that all you need is spin-orbit coupled semiconductor and SF superconductor. That will do the trick also if you apply spin splitting somehow. And these are things a lot of people are working on. The underlying, all of them have this topological degeneracy I was talking about. An underlying qubit is the same for all of them. There is this quasi-particle that is Majorana. So let me just talk about the fractional quantum Hall. A lot of people believe, including myself, that the 5-half state that was mentioned in an earlier talk, this is the only even denominator fractional quantum Hall state known in nature for single layer, and one of his discoverers is sitting in the audience, Jim Eisenstein. This is in 1987, and this state, this 5-half state, is thought to be a non-Abelian, one of these multiple ground state degeneracy state. This is the wave function, Moore and Reed wave function. This is in Spenta's honor. I'm just showing you the Wozeminal, the Witten action. It's John Simons, exactly. The point is that Witten wrote this famous book. John Simons, everybody thinks John Simons is always famous. John Simons was an obscure subject in math. It was. That's what, the reason is that it was a very technical thing, and people thought it was very beautiful, but people didn't know what it was good. Wilson showed that John Simons' theory has deep connection to topological quantum field theory. And we have never looked back after that. And so this thing is a direct example of that. And it was already mentioned that what you have here is this composite fermions. Remember, composite fermions, they're spin polarized. If you take spin polarized system and try to form a superconductor, simplest superconductor you can form is P wave, right? Because it cannot be S wave. For S wave you need spin up and down, because spin part then cannot be antisymmetric. So here, once you have both spin up, then you can have P wave, and P wave is the simplest, so it's a P wave superconductor. So that's what happens here first. And then I'm going to go through that. This is another animation showing what you do. Here are your Majorana Fermion. You just braid them correctly, and then you measure the final state. The fuse, they give you something else. You measure the final state, and if you see the result you expect, you have done your computation. And if anybody ever does that, I'll be a very rich man, because I hold a patent on this thing. Okay? So, Steve, remember, if you come up with a topological thing, you'll get some good dinners, because I'll be a very wealthy man. Okay? So I hold a patent, but I'm not holding my breath to make this money. Okay, I have to be honest with you. Okay, we wrote a paper, and then Microsoft took a patent out on this thing. So why is it that all these things are in 2 dimension? I mean, I'll be done in 5 to 10 minutes. So this is now, for the expert, this is a very trivial thing. I would not go into great details, but I want to tell you that there's a fundamental difference between 2 dimension and 3 dimension. There are no knots in 3 dimension. If you take a sphere, put a knot, you can just slip it out. You can make it continuously vanish, right? You just take it out, it vanishes when you take it out. But if you put a knot in 2 dimension, there is no way to make it vanish without cutting it. So knots are non-trivial. Amazing thing is that, you always say, I certainly say, I was born too late. All the simple things are done. I can never be famous because all the easy things somebody else did long time ago. Okay? But this thing was not realized until 1979, that 2D is different from 3D. That in 2D, you learn in your quantum mechanics class, knots are there. So 2 dimension and 3 dimensions are very different. In 3 dimensions, you cannot have any knot in world lines. In 2 dimension, you do. 2 dimension, the fundamental thing is Bragg group. In 3 dimension, permutation group. Bragg group is much richer than permutation group. Bragg group allows for various fractional particles, all kinds of things. That does not mean they have to occur in nature. It's allowed. It may turn out nature is very unkind. All you have in 2 dimensions also just fermions and bosons. You don't have anything else. But unlike 3 dimension, in 2 dimensions you can have other objects. Those objects are called anyons. And in some situation, those objects, these anyons could be even non-Abelian. And if they're non-Abelian, you can do quantum computation. So I think I'm going to stop here because I do not like going over time. It's 1 hour. But let me tell you that quantum computation is just an excuse here. Okay? Really, it's an excuse. And people who attack quantum computation really do not quite appreciate the beauty of what is going on here. Here are these incredibly deep theoretical ideas. Topological quantum field theory. I even have a paper with the word Jones polynomial in it. And I met Von Jones. I talked to him about it. He said he really likes it. And I said, which part do you like? The mobility part? Because that's my contribution. Okay. So point is that, it's all those things come into the theoretical description of this subject. Literally they do. Okay. And these things, which should have been the territory of mathematicians and very fundamental physicists, now are getting connected with things like high mobility gallium arsenide, lithography, superconductor, nanowire, semiconductor nanowire, coded at 5 fractional. They're really getting connected together, and pure mathematicians are worrying about MBE growth, and I'm not really worrying about, but I'm trying to learn topological quantum field theory. Not that much knot theory, topological quantum field theory. This could only happen because of this new paradigm of topological quantum computation. If there's no push for topological quantum computation, I do not think I would ever learn any of these things, because what is the point? I already understand 5 fractional quantum Hall effect from a wave function viewpoint. I don't gain anything by saying is SU2 level 3. That's just putting a jargon on it. It does not increase my understanding. But on the other hand, if I want to do quantum computation, this jargon is very important. So, the point I want to emphasize is quantum computation is a huge subject. And this huge subject has principles, paradigms, physics, mathematics, which could not have been done without the excuse for quantum computer. We may or may not build a quantum computer someday. I hope we do. And even if we build, it may not be particularly useful for anything. But in the process, physics and math will be incredibly enriched. And I think many of us are doing it. I think I speak for many of us who work in this subject, doing it for this fun ride. Of course, would be delighted if a quantum computer is built. But that's one of our many goals. And with that lofty pronouncement, I will stop. Thank you very much.
Thank you very much for the wonderful talk. It's open for questions.
I have a mundane question about your J
Sure.
as a function of R.
Yes.
You showed that interesting oscillations,
Right.
which happens at the level of lattice spacing.
Correct.
And it gets decayed beyond the impurity wave function
Right.
side. Now, there seems to be a message to a very different subject, namely dilute magnetic semiconductor,
Yep.
where you want ferromagnetism, but according to you will
correct,
be...
Correct. But those oscillations are different. These are not RKKY oscillations. These oscillations have nothing to do with RKKY oscillations.
But still, they have spatial...
That's correct.
oscillation.
That's correct. In
And
fact, our referee
implications
asked
are-
is that these oscillations are arising only from the fact that this is not a many-body problem, only from the fact that silicon has 6 valley,
There are
so
wave
starting
vectors.
wave function has this trigonometry. So that's why I do not understand why people who are working on this in the 50s, they should have known. But I think experiments could not really see this. But now I think STM will see it. You know, if somebody does STM in phosphorus silicon, they will definitely see these oscillations. I have no doubt about it, that these oscillations will be directly seen. And the problem here is that what this is saying is that, let's say your 2 qubits will be 500 angstroms apart. What it's saying that you'll put 10,000 qubits separated from each other 500 angstrom, but the precision of placing the dopants have to be better than 1 angstrom, better than 1 angstrom. Otherwise, you know, you have to characterize each qubit. And that will be, you know, the great advantage of silicon was that everything is very precise. This is not an example I'm giving to say silicon is bad. It's an example I'm giving to say how quantum computation allowed us to do some beautiful, simple science, which could not have been done otherwise. Okay? I'm sure experimenters are very clever. They'll find a way around it. For example, I did not talk about it. These are slides I skipped. That all you have to do is somehow create the values to split. Remember, it's arising from the valley. If you can make those values split, so one way you can split the values, and that's what people in Australia are doing, you go near a surface. So remember, there are 6 equivalent minimum. So if you go near the surface, 4 of them immediately get lifted. You have just 2. So then it turns out you can split these 2 by a variety of techniques, and that's what people are working on. So after our work, now everybody knows that in silicon, you must have value splitting to create a quantum computer. So if they don't have a large value splitting, they don't even look at the sample. But it turns out in each sample, there is some value splitting. So this is, you know, this is the message from this. But this is not RK2Y oscillation. But I understand what you're asking. Thank you. Jim?
I have a question which is going to reveal my ignorance of the subject, but you talked at the beginning about quantum error correction.
Yes.
When you build a quantum computer and you're trying to solve a problem, the answer of which you do not know, is it always obvious that you will know when an error has been produced?
It's a good question. You have to measure. You have
to measure to find out that you've made a mistake, that an error, I mean, it's all going to work out in the end, Steve?
Yeah, maybe Steve knows a better answer than I do.
So
it's a...
You don't actually have to measure. There's a way to... So an error is entanglement with something that outside your logical space, and entropy has entered your computer. And some non-unitary thing has happened. So you have to do something non-unitary to remove it. One thing is measurement of some clever thing
this is what
that
I thought only one.
Measures the error and doesn't mess up the state somehow and allows you to correct. Or there are these schemes for pumping the entropy out, like in a refrigerator, in which the bath carries away the entropy and the quantum information is still there.
Yeah, that's all pretty hard to me. But yeah, so it's a good question. Meaning, don't try to build one.
Any more?
Please.
In terms of experimental realization of Majorana fermions, you showed this Delft group.
Right.
And also you heard about the 5/2
Yes. Yes.
even odd effect.
Right.
So are there any other things, and among them which is standing?
Right. So probably what you're asking, 5/2 Majorana, which is charged, the quasi-particle, sigma quasi-particle, is that also established or not? This is a difficult question for me to answer because I spent a lot of time on 5/2. So for a long time, we thought 5/2 manipulating this sigma particle, which is the Majorana particle, is very close. It has turned out to be very challenging. I'll give you my reason for why I think so. I'm actually not working on 5/2 anymore. The reason is, as was explained by Jim, all the action in quantum Hall is at the edge. So all our action is on the edge. So these quasi-particles are moving on the edge, and that was the advantage. If you look at our qubit, which I didn't discuss at all, which is very close, I'll show you. In our qubit, what we showed, the insight on this qubit was that the current is nothing other than motion of quasi-particles. Okay, that was our insight. And once you know that, then you can form interference pattern by having some gates and letting the current move any way you want. So you put a dot here, you localize a quasi-particle here, another dot there, localize a quasi-particle there, and you can then make the correct pass to form your Jones-Hart polynomial that comes from math. Okay, so we thought it's really trivial because the current is there. All you have to do is just distort the path, and we have our quantum interference, right? What has turned out, this age is not simple like this at all. So all the age experiments among the people here, Charlie has done some, Bob Willett has been working on it, Maury Heibloom, there are a huge number of experiments. The verdict from those experiments, this age is not simple like what I'm telling you here. You know, the charge of this quasi-particle, which is the correct Majorana, is E/4. We don't even know, charge has been measured, and there's a very famous paper from Maury Heibloom's group. I think Vid was involved in it, and the charge was E/4. But then later experiments showed it depends on all the details. The charge could be basically anything, you know. And the age is turning out to be what I believe is that 5F is a non-Abelian Moore-Reed state. So it's a chiral POF superconductor, exactly like what Dev group is working with. But the age is much more complex than this pristine age, because if the age is very smooth, you'll have every single Landau level go through it, and who knows what's going on. So after 6 or 7 years of intensive experimental effort, I would say that many of us have become slightly discouraged about the possibility of using this but we have not given up. What is the advantage of superconductor? I'll tell you that tomorrow. There are some obvious advantages, because where the Majorana is extremely well defined there. At the end of a where, it can't be any simpler than that. If you see the Majorana, you know exactly what it is. Okay, there is none of this problem. That's why there is a lot of excitement in the nanoware, this superconducting Majorana. Other advantage, in principle, you can work at even 5 Kelvin. If your superconductor is niobium, 10 Kelvin, your induced gap could be 5 Kelvin, so you can work at very high temperature. This is why the community has moved to Majorana in superconductors. But I think 5F is still a very strong candidate within the caveats I just told you. I don't know, is this what you're asking? Yeah.
Have you patented the
patenting is a very expensive proposition, okay? So I have not patented it, but what happened is that Roman Luchin, who was involved in this work, went to Microsoft. So he has patented several of those. If it goes somewhere, I'm hoping he'll give me some of that money. But yes, there are patents. I'm not involved in them. Yeah, there are patents.
Any more questions? I have a small question.
Please.
So it's I think you might be covering it tomorrow, but still, I'm really curious about it. So between the Merkley Telluride quantum wells, where you have the protected states, and
you mean the quantum spin Hall?
Yeah, that's right. Mm-hmm. And the topological insulators where you got the surface
right.
states. Which one do you think have a better control if you want to eventually form a
Majorana?
Yeah.
So right now, I would say topological insulators. Okay, first I have to make some assumption. I have to assume that Lawrence Molenkamp, given that he has now owned something like n number of prizes with n going towards infinity, so I have to start with the assumption he really saw quantum spin Hall. Nobody has reproduced the data, but I believe the data, and let's say that's a correct experiment, and he has seen quantum spin Hall. Then I would say that's the more likely candidate right now. All the experiments are much more difficult in that. Why? Because topological insulator, the problem is your bulk conduction. If you have bulk conduction, if this anion is in contact with the fermionic bath, it will leak away. Because remember, this anion is half electron, half hole. You can't put it in contact with the fermion bath. It will immediately, all this immunity and so on, there is no immunity at all. It will instantaneously disappear. Okay. So right now the problem with topological insulator is bulk conduction. So if all these bulk conducting states can be eliminated in, let's say, bismuth selenide or some other TI material, then that immediately becomes, I would say, a very strong candidate at the same level as this spin order cup. Okay. But before that, I would have to say quantum spin Hall with a superconductor that Amir, I think, wants to look at. Okay. But this is just a question of time. I mean, once bulk conduction is eliminated, then that becomes. So that would be my answer. Okay. Unless somebody disagrees with me. I'm trying to give a very careful answer.
Okay. Any more questions?
Yes.
The question is related to what Arindam asked. You mentioned that the materials which have high spin orbital coupling or the topological insulator, both are candidates for Majorana Fermions. And the topological insulator material are one of those which have strong spin orbital coupling.
Yeah.
So if we forget about the bulk doping.
Yeah. This is the question I have been asking experimenters and material scientists to understand it. I do not know much about bismuth selenide. Whether bismuth selenide can be used as a semiconductor with high spin orbit coupling, and then do the things. I cannot answer this question. Somebody who understands bismuth selenide better has to answer that question. That forget about the only thing is that you have to create two-dimensional states there, and you may be able to create two-dimensional state just by creating an accumulation layer. You do not even need to use the surface conducting state. But I cannot tell you, yes, that would work. I'm not an expert on the subject. But as long as a two-dimensional electron gas with strong spin-orbit coupling, and you can apply a Zeeman field to create a spin splitting, it should be okay. But you cannot use the surface conducting state because there is no spin. Any semiconductor will work. So to the extent it's a semiconductor, in principle, yes, but in practice, I do not know. Others have thought about this question too, that can we just use the large spin-orbit coupling of bismuth selenide, forget about its Z2 topological properties. And in principle, yes, in practice, I do not know.
Any more? Okay. Maybe the last one.
When we increase the number of non-Abelian particles in my 2D sample, do we increase the number of qubits, or we just increase the dimensionality of the?
Okay, so this question will be answered in different levels. Of course, each one of these localized quasi-particles is a qubit. Each one. So you increase the number of quasi-particles, you increase the number of qubits. But they are nuisance if you do not control them. So suppose in this our patented thing, we say that there is exactly one of those quasi-particle here, then it's a nice qubit, but if there are 5 others here that you don't know of, then when you braid it, you go around it, you are doing a computation, but this is not the computation you wanted to do. Okay? So whether these quasi-particles are wanted quasi-particles that you are controlling or unwanted quasi-particles that are just in the environment make a huge difference, because the computation that you want to do depends on exactly what braiding you are doing. If you have just one quasi-particle, it's one kind of braiding. If you have things that you do not know. So indeed, each quasi-particle is a qubit, but this qubit could be source of an error if they're unwanted. That's answer number 1. Answer number 2 is that if these qubits are very close to each other, this is something I'm going to talk about tomorrow, then they no longer are qubit, because it's only when they're very well separated from each other, then they are this topologically degenerate object. It's like, as you know, when you have many electrons, you cannot describe a many electron system as fermionic, because many electron is neither fermion, nothing, it's just quasi-particle. Similarly here also, if the 2 quasi-particles are close by, then they cause a splitting. They are not at 0 energy anymore, and they are no longer non-Abelian. So you cannot have too many quasi-particles, because then they'll be jam-packed, and then even if you control them very well, you are not controlling. So there are issues. Okay.
I couldn't see the 0 state and 1 state in this system.
That you have to wait tomorrow. You couldn't see it because I didn't show it to you. Okay. It's the 0 state and 1 state that this, since you asked, I'll give you the answer. This Majorana, the Majorana that Leo Cohn saw, and then Charlie Marcus has seen it recently also, is in common language a superposition of half an electron and half a hole. Okay. So it's because it's a superposition of half an electron and half a hole, it's equivalent to, and so that means it can be occupied by an electron or not occupied. So that's basically the qubit, either occupied or unoccupied. Okay, so it's parity. That's the qubit. Okay, it's a very simple qubit. That's what it is. But I'll talk about it tomorrow.
Well, let's thank Sankar again for the talk. And we break the session today, and we meet tomorrow at 9.